Alright, so this is going to be an overview of how to analyze the data from the lab. You can see here, this is the CSV file that you should have gotten from the lab. We've got two columns of data. This one is time, and this one is the experimental voltage measurements. So I'm going to label these columns so we remember what they are. And then notice that I saved this as an Excel file rather than the CSV that we had before. Okay, so the next thing we need is over here, we want to make a column of theoretical voltage. And to do that, it's going to be a column that lines up with this column, and the equation's given right here in your lab handout. And you can see it's a function of 5 different things that are in here. We've got VO, VA, T, TI, and tau, the time constant. So T, this T, is this time column over here. The rest of these are constants that we have to figure out by looking at the experimental data. Okay, you can see I set up a place to type the numbers when we figure them out. The 4 constants we need are V0, VA, TI, and tau. And remember from the equation over here, in most textbooks there's some assumptions, and normally V0 here is taken to be 0, TI is also taken to be 0, so that if you look at the graph, this would start at 0 volts, and at time t equals 0 it would rise up. Because of the experimental data we have to add these constants in, so these are just shifts that we need to account for. VA is the amplitude, how much the voltage rises, and tau is the time constant. That's the first order parameter. So let's look at V0 here, the first number. This is the bottom asymptote that we've got in the graph right here. The easiest way to find this is to look through my data, either by graphing it or just by scrolling and looking for a voltage that's a constant, the small number that we're going to have a lot of. So I'm going to start scrolling down here until I see some small numbers. Somewhere in here I'm thinking I've got a lot of these numbers that are about the same. So right in here we've got these minus 5.1 sort of volts. That's going to be the low number that I'm going to use. So I'm just going to call it negative 5.1. You could average a few of these, might be a better approach, but anywhere in there is going to look just fine. I'm going to type that in here, minus 5.1 for V0. The next thing we need is VA. To get that, if we look over here at the plot, you can see this top asymptote, this voltage, it rises to V0 plus VA. At the top. So I'm going to get that again by just reading through my voltages here, and I'll find a high voltage that will get a lot of the same values, and we'll use that number for VO plus VA, and then I'll subtract VO to solve for VA. So I'm going to scroll down again. There's all my minus 5s. Here's where the voltage is rising. It's rising up to in the 7s here. Somewhere it'll start to go back down again. So yes, here it's going back down. So somewhere in this range, it's the high voltage that I'm looking for. So 7.29, 7.288, something like that. Let's call it 7.288 volts. You could again average those if you wanted to take something. So 7.288 volts is, again, that's VO plus VA. So in order to get VA, I need to subtract one from the other. So that minus that and I've got my VA of 12.388 volts. So my plot goes from -5 to 7.2 for a rise of 12.388 volts. Okay, those are the voltage, amplitude, and offset. Now I need to get the time, offset, and then tau. So the next thing is TI. So TI is defined down here on the x-axis as the time when the voltage just starts to rise. So it was hanging out at these -5.1 levels, and then just when it goes up to there, and I can read the time right off the column. I could also zoom into a plot if I wanted to, but I'm gonna look here. So again, I'll go down to my -5.1s. Here's this initial V0, VO voltage. Holds it constant for a long time. And here it's starting to rise. These are getting larger. So somewhere in this range, -5.08, I see it for quite a while. And then right here is a big jump. So I'm going to say 0.465 is my TI. There we go. The next thing I need to get is the time constant tau. And so one way to do that is to know the resistor and capacitor values of your filter and just calculate it. So if you know what those are, you can calculate it. In this experiment, we didn't know what the resistor and capacitors were. They were on that board that we used. So we're going to determine it experimentally. If you use this equation, when t equals ti plus tau, one time constant after the start, you get a ti plus tau minus ti divided by tau. So you get a 1 minus e to the -1 up here. So plug in ti plus tau for t, and you'll see that's where this VO plus 0.63 VA comes in. 0.63 is 1 minus e to the -1. So I can calculate this voltage. I can find when my voltage plot crosses through that voltage, and that time will be Ti plus tau. So I'm going to calculate this first. VO plus 0.63 times VA, 2.7 volts. Then again, I'm going to scroll down through here somewhere after TI. .7044. Scroll down. Somewhere in this range. So between these 2 points, we go through 2.7044 volts. So I could interpolate these, or I could pick one. I'll interpolate between these 2 points. What I want to find is the time when it goes through 2.70 volts. Okay, so I did some interpolation on my calculator, and I found 2.7044 volts at 0.4852 seconds. So I'm going to go back up to where I'm recording my data. Ti plus tau is 0.4852, which means my tau is this minus Ti 0202 seconds. The rest are in volts. So these are the constants that I need now to calculate my theoretical voltage. I'm going to do one thing here. I'm going to highlight these, and then I'm going to go to Data, Formulas, and create names from the selection. They're in the left column. Now when I click on this instead of being F12, this is called VO, and this is called VA, TI, and tau, so I can use them straight in my equation. So now my equation's over here. V is going to be equal to VO plus VA times 1 minus e to the negative t, which is over here, minus ti divided by tau. Notice that this goes to times 10 to the 11th. Before ti here, the theoretical curve goes way down to negative infinity. So this isn't wrong. We'll see what it looks like when I make the plot in a second. I'm just going to copy this formula out. Didn't work. Let's see what happens here. So here's the portion where it's trying to follow the theory. Here's the portion before TI. So I'm going to graph all of these and I'll show you what it looks like. Alright, I'm going to make a scatter plot of this data. You can see again this goes to some really huge number, so I don't want that to be in my data. I can either just change what I'm plotting here, rather than starting at 23, I can start it later. That's probably what I'd like to do, or else you can just change the axes. But if I look down here, I don't really care if I plot anything before here, so I'm going to start it at 488. Go from then. Row 488. That's where my good data starts for the theory. The experiment is fine, so I'm not going to mess with that. Theoretical voltage, if I click on there, I can change this. See what happens. There we go. If I change that one to be a line, and now you can see, finished my plot. I've got experimental as the dotted data, theory as the solid line. They line up really nicely, and you can see all of my constants over here. I put the time constant up in the title because it's really important to spell that out. And remember that all of these will be different for your experimental data. The time constant is different in my data, and all of the voltage asymptotes will probably be different with yours as well. Good luck, and get in touch with me if you need any further help.